it's Coach Fred here today, and today we're going to be talking more about polynomials. And how can we deal with polynomials or solve polynomials if they're not factorable? So what do we do if a polynomial is not factorable? And that's going to happen. So the polynomials we've looked at up to this point are quadratic. So if a quadratic isn't factorable, we have some tools. We could complete the square. Right? We could complete the square. Or we could use the quadratic formula. Okay, so we have these tools. We have some tools with polynomials as well, but they're not as formal as completing the square and the quadratic formula. So let's talk about that. What can we do if it's not factorable? Well, let's think about what factoring is, okay? So if I factor the number, say, 27 into two factors, that means I'm breaking it up into multiplication. So I could say that 3 times 9 are factors of 27 because 3 times 9 gives me 27. Well, way back in pre-algebra, when you were learning about the numbers and how they related to each other, you could also find one of the factors if you had the other factor by division, because 27 divided by 9 would give you 3, so the missing factor, and 27 divided by 3 would give you 9, okay? So let's think about that with a quadratic. If I gave you the quadratic, say x squared minus 3x minus 10, and if I knew that one of the factors was x minus 5, then couldn't I think about doing x squared minus 3x minus 10 divided by x minus 5? Yes, I could. And this one's a little bit easier because you have that tool of factoring now of quadratics. So you might be able to say to yourself that, you're trying to get the same structure as this. So we know that our last digit has to be 10. So it would have to end in a 2. Our first digit has to be x squared, so it would have to be an x. And then our middle term needs to multiply to -3, so that -5 would have to be multiplied by +2 to get a -3. So that's what factoring means, but we could use division here as well. Okay, so let's think about division a little bit, okay? So here is an example of long division that you haven't done in a really long time. 949 divided by 23. That could also be written as 949 divided by 23. So I think it's important to know the terminology here, okay? So we call 949 the dividend, and we call 23 the divisor. Now when you think back to division and doing this, if the divisor goes evenly into the dividend, then that would mean it's a factor. If the divisor does not go evenly into the dividend, then you'd have a remainder, which means that it's not a factor of the number, okay? All right, so let's try this. We're going to go through this long division here and see if we remember what to do, okay? So you may want to write down your steps if possible. Okay, so first I'm going to check to see how many times 23 goes into 949. All right, so let's just play around here. I know that it might go 4 times because 20 times 4 is 80. So that's how I start with it. So I'm going to try 4. So then I multiply 4 times 23. So 4 times 3 is 12. Carry the 1. And then 4 times 2 is 8 plus 1, so 9. Okay, and let me actually erase that line because it's going to get in my way a little bit. So then I'll do that again, so 92. Okay, so then we subtract those 2 digits. Okay, so I'll put that there. Subtract and 23 into 94. Okay, then we subtract. So 94 minus 92 gives me 2, and then bring down the 9. Bring down 9 and then repeat. Okay, so I'm going to say how many times does 23 go into 29? It goes in one time. So we get 23. We subtract and we get 6. And so 6 is what we would call our remainder. So we would, if we were back in pre-algebra, we would write that as 6 over 23. So 949 divided by 23 would be 41 and 6/23. Okay, so that tells me 23 is not a factor, of 949, okay? All right, it's actually an algorithm, okay? So the algorithm works out to be the dividend divided by the divisor gives you what we call the quotient. You've heard that term before, plus the remainder over the divisor. So look at that. Dividend, 949. Divisor, 23. Equals quotient, 41. Plus remainder, all over divisor. Okay? Now, the plus sign's not there because I really don't have to do it if it's a number. Okay? All right, so let's see how we can use this to perform this new thing that you're going to learn called polynomial long division, okay? So polynomial long division follows the same process, but instead of numbers, we're going to use variables, okay? So when you divide a polynomial by a non-zero divisor, you're going to get a quotient polynomial and a remainder polynomial. Okay, so this isn't all that pretty here, so I'm going to actually rewrite it, okay? So 4x plus 1 into 8x squared plus 6x plus 3. Now I'm using a quadratic here, so it makes it a little bit easy. The dividend, just so we're clear, has to be in standard form, and there actually can't be any missing variables, which we're going to talk about in the next one. All right, so the first step, and this is where it gets a little tricky, I'm going to see how many times 4x goes into 8x squared, or think of it like this. 4x times what would give you 8x squared? All right, so hopefully you're saying 2x. Now I need to put that on the quotient line, but above I want it to line it up with the number that has the same variable. So see, this is 2x. I want it to be above the 6x. Okay, then I need to multiply 2x, okay? Actually, let me do this. Let me use a highlighter. I need to multiply 2x to 4x plus 1, okay? I need to multiply 2x to 4x plus 1. Okay, so let's do that. 2x times 4x is going to give me 8x squared, and then 2x times 1 is going to give me 2x. And then I'm going to subtract. Now remember, when we subtract, we have an expression here, so this becomes negative and this becomes negative. I always put that line there to help me. So your 8x squareds are going to simplify to 0 or cancel out. And then I do 6x minus 2x, which is going to give me 4x. So now I bring down the 3. Okay, and now I ask myself, 4x goes into 4x how many times? Or 4x times what would give me 4x? And hopefully you're saying 1. And so then I multiply 1 to 4x plus 1, getting 4x plus 1. And then I subtract, so minus, here, let me use blue here so you can see it. And then 3 minus 1 gives me 2. My remainder is 2, so I add it to my quotient, so 2 all over 4x plus 1. Okay, now that looks hard, but it really is just the algorithm of division, right? It's just division. Now, what does it tell me? Well, first it tells me that 4x plus 1 is not a factor of 8x squared plus 6x plus 3. Okay? All right, what else does it tell me? Well, this number actually means something. Okay? It relates to this number and to the graph of the function, okay? The graph of the function 8x squared plus 6x plus 3. So let's look at that. All right, so here I have the graph of 8x squared plus 6x plus 3. That was our original dividend. And then if you look, I plotted it, and I can see that on my graph, negative 1/4 is actually equal to 2. Okay, so let's look back at our question here. Our original divisor was 4x plus 1. If I actually found its x-intercept or its root and set it equal to 0, it would actually be negative 1/4, right? X would be equal to negative 1/4. So what this is telling me is that at an x of negative 1/4, the y on this graph is 2. So because I got a remainder, it's not at 0, it's not on the x-intercept, but at that point, that x-coordinate, my result is going to be 2. Now, if we had gotten a 0 here, then I would know it went in evenly, it was a factor, and so both the original divisor and the quotient would be the x-intercepts, or would lead me to the x-intercepts of the graph, okay? Hopefully that helps. Okay, so this was part 1 because it's been a little long, and you're going to go on to part 2 to see example 2, okay? Have a great day.